So should we wait for 2-3 minutes more, or?
Sir, actually, Komal is sick right now, so she might not
Oh,
be able to attend the class.
okay, okay. So who is left? One more person is left, right?
Yes, sir.
I think, sir, we can start.
Okay. Okay, so let me share my screen. Okay, so today I would like to start a very beautiful topic known as elliptic curves. There are some beautiful books on this topic, especially for the reals and complex numbers. And for finite fields also there is enough material because of their applications in cryptography, and the crypto system that are built on elliptical crypto system, they have a smaller key length, so they are quite useful actually in terms of applications. So before starting this, let me uh, recall some basics. So suppose C is a curve, plane, curve equation over K. So K is, we can call it as a field, some field, should be reals or complex or finite field and so on. This is a plane curve equation over K. Then first I would like to say what is the point of singularity. A point of singularity on the curve C is a point h comma k in K square for which f of h comma k is equal to 0 and delta f over delta x hk is 0 and delta f over delta y related at hk is 0. So then such hk point is known as point of singularity on the curve. Okay. So a curve is called non-singular or smooth if it contains no points of singularity. Okay. So then we say that a curve is singular. So curve is non-singular, is smooth if it has no point of singularity. So a singularity on the curve fxy is equal to 0 is a point for which f of hk is equal to 0 and del f over del x and del f over del y at the point hk is equal to 0. Okay. So what is elliptic curve actually? So basically, all these curves that you come across, like parabola, ellipse, hyperbola, or any plane curve that you look at, these curves are known as curves with genus 0. Genus is a measure of a smoothness of these curves, and it turns out that all these curves which has genus 0 can be parametrized. For example, you can find parametric equation for this. For example, circle, right? Circle is a curve, but x equal to sine theta and y is equal to cos theta is a parametric representation. Theta is a parameter, right? So each of these curves with genus 0 are basically uh, you know plane curves. Elliptic curves are curves for which curves of genus is equal to 1, and hyperelliptic curves, which are having genus more than 1. Okay, so these are the very loose definitions of elliptic curves. When genus is 1 or more than 1, then they are known as hyperelliptic curves or elliptic curves. Okay, so let me give you uh, some examples. First of all, I can describe what kind of singularity uh, might be there. So I recall some definitions more here. Suppose A is a n by n matrix. Okay, now I am assuming that scalars are all reals. Okay, so this matrix is called positive definite. If for every non-zero column vector v is equal to v1, v2, vn, so column vector of size n, we have v transpose A v positive. Okay, so a matrix is said to be positive definite if for every non-zero column v, we have v transpose. So basically, this is v transpose AV is positive, then it is known as positive definite. Similarly, a matrix is said to be negative definite if for every positive non-zero column v, we have v transpose AV negative, then it is known as negative definite. Okay. Now, for any such curve, we can define Hessian of the curve. The Hessian matrix is there. Hessian of F is delta square F over delta x square, delta square F over delta x, delta y, delta square F over delta y, delta x, del square F over del y square. This is the Hessian. Okay. For any curve F, we can find the Hessian, and we can then classify the singularities as follows. Okay, so if basically a point P on C, a point of singularity P is point of singularity, P is a cusp if Hessian of F at P has determinant 0. If the Hessian matrix has determinant 0, then this point is known as cusp. A point P on C is a loop. We call it as a loop if and only if Hessian of F at P is is negative definite, right? And P is an isolated point if and only if Hessian of f at P is positive definite. Okay, so a point P, the point of singularity on a curve, can be characterized as cusp, loop, or isolated point, depending upon the nature of the Hessian of the Hessian of f at the point P. If so, this Hessian matrix, you compute this at point P, right? So if P is h comma k, you can substitute, you compute this and then substitute this value and then compute this. Okay, and then if the determinant is 0, then this is known as cusp. So if determinant is 0, cusp, okay, then negative definite, then it is a loop, positive definite, it is an isolated point. Okay, this is coming from calculus actually of multiple variables, so I think I'm not going into details of these things, but this is how we define. Let me give you an examples now. Let me give you an examples of these things. Take k to be a real numbers. Field is real numbers. And suppose the first curve that we take, y square is equal to x cube. Now y square is equal to x cube. You can check that 0, 0 is a singular point, is a singularity. Not only that, you can check by calculating the Hessian, and it is a cusp. Okay, so this will be something like picture will be something like this. It's a cusp here. You see, this is 0, 0 is a point of singularity, and it is a cusp. Similarly, if we take b to be equation, y square is equal to x cube plus x square, then 0, 0 is a loop, again a singularity. Okay, and this can be described by somewhere here. Sorry, this is here. So this is 0, and here somewhere it is 0. 0, 0 is here, you can see. So at origin there is a loop. Okay, loop. This is a singularity. Okay, and third, if we take C to be the curve y square is equal to x cube minus x square, then 0, 0 is a isolated point, isolated singularity. So that means, the Hessian we can calculate, and Hessian of f at p is positive definite. And in terms of picture, if you want, the picture you can see this is 0, 0. It's an isolated point, and the curve is going something like this. Okay. So I gave you 3 examples of the singularity here. In each of these cases, point 0, 0 is a singularity, and in one case it is cusp. So this is cusp, loop, and isolated point. Okay, this is how we describe these singularities. Now, I think elliptic curve. What is elliptic curve? Actually, now I'm ready to define what is elliptic curve. So, elliptic curve is a curve defined by the following equation. So we assume that K is a field. Okay. So elliptic curve E defined by equation y square plus a1 xy plus a3y is equal to x cube plus a2x square a2x square plus a4x plus a6. An equation of this form is known as Weierstrass equation for the elliptic curve, right? And ai's belongs to k, provided it should not have a singular point. So it should be smooth actually, If this kind of equation does not have a singularity, as we described earlier in our examples, then such kind of equation give rise to what is known as elliptic curve, right? So genus of such elliptic curves is 1. One important thing, if you look at the points of all those points which are part of this curve, they form a group. It means if you take a point P and take another point Q, P plus Q is again a point on the curve, right? And also there is a point at infinity which can be added to which acts as an identity element, So P plus that point at infinity O will be nothing but P, the same thing as O plus P. So those kind of things are there. So I'll talk about this group business later on, but now let me give you some examples. Okay, so suppose y square is equal to x cube minus x. One thing I should mention here, in each of these singular points, the tangent is not uniquely defined at the point of singularity. You cannot define tangent uniquely at each of these points. This is something you should keep in mind. Okay, if y square is equal to x cube minus x, okay, so I can plot it how it looks like. This is point at origin and something like this. So there are two disjoint components. The xy plane. Okay, and so this is known as broken handle. This closed form of loop is known as broken handle. So two disjoint components in the plane is here. This is one such example, right? Another example I can take y square is equal to x cube minus x plus 1. In this case, if we draw the picture here, something like this. Okay, so handles are not discernible here, So this is a single component here, single piece. Okay. Third example. Y square is equal to x cube plus x. In this case, this is origin. And the curve is something like this. Okay. So in each of these cases, I should mention that in each of these cases, we have each such cases, del f over del x and del f over del y does not vanish simultaneously, okay, at every point on these curves. Therefore, tangent is defined at every point on these curves. Okay, so tangent is defined here, here, here. In case of singularity, it is not uniquely defined, right? I mean, the tangent cannot be defined at the point of singularity, but here it is defined at every point. Okay, so now let me give you a couple of examples of elliptic curve. So remember, this V star equation is very, very important. That y square is equal to y square plus a1xy plus a3y is equal to x cube plus a2x square plus a4x plus a6, where a1, a2, a3, a4, a6 are part of this field K. You know, there are elliptic curves over finite rings as well, but that's okay. We are not studying it. Let us look at some examples. Okay. Suppose our field is F17. Field is 17 number of elements. So let us look at this equation: y square is equal to x cube plus 5x minus 1. So my question is it an elliptic curve? And please try to answer me. Yes, answer me. Is it an elliptic curve over the field F17? Yes, any answer? Ajit,
Yes, sir.
Praveen?
By the equation, we can find the similarities there.
So what we need to check actually? At least you tell me what you need to check. So if equation is given over some field, first question I would like to ask: is it an elliptic curve or not? So what we need to check?
So using the wave stress equation, we can find the one-to-one mapping.
No, actually that is not sufficient. Remember, there is a condition on the V-star equation. It
Should
should
not
not have a singular point. So I need to check whether it is having a singular point or not. Okay. If it is having a singular point, it is not going to be an elliptic curve. And it turns out that you can verify that 20.20 is a singular point here. Okay.
Yes.
Singular point means, all those conditions are satisfied. Remember, this f of h comma k is equal to 0 and del of, these conditions are satisfied, for this point, right? So this is not, since there is a singular point, this is not an elliptic curve, right?
Right.
Okay, so this is not an elliptic curve. It contains a full singularity. In fact, in the right hand side, we can actually, this factorization at the right hand side tells us many things about the points. So x cube plus 5x minus 1 can be written as x plus 15 whole square x plus 13. Okay, modulo 17. Okay, so this is a possibility. So, but so this is not a, because it contains a singular point. So over F17, it is not an elliptic curve. But on real numbers, y square is equal to x cube plus 5x minus 1 is an elliptic curve. You see, you change the field, then it becomes, there is no singular point there. In fact, in that case also, this equation x cube plus 5x minus 1 has no multiple roots. Okay, so this side, the right hand side, tells us a lot about the nature of the curve. Okay, so basically the curve is elliptic curve over the real numbers. Okay, now let us take another example here. If I take the curve E1 to be y square is equal to x cube minus 5x plus 1. I've changed it slightly with minus 5 here. This is a non-singular curve, you can check. It is a smooth curve. There is no singularity. Non-singular curve. How will you find this? You just put fxy is equal to 0 and see, what are the points, and then, compute del f over del x, del f over del y, and, do all those calculations. So this is non-singular curve over f17 with 15 points. 15 points are there. So I can list those points as 0, 1, 0, 16, 2, 4, 2, 13, 3, 8, 3, 9, 5, 4, 5, 13. 6, 0 is an important point here. I will talk about it. And then 10, 4, 10, 13, 11, 6, 11, 11, 13, 5, and 13, 12. So these are 15 points. Actually, how to find these points is interesting. There are interesting algorithms how to find these points on the elliptic curves, and there are certain bounds known as hash bound. We will talk about those things later on. But these points are there. So only one point. This point is there on the elliptic curve, for which y component is 0, and that can be seen also from the factorization, because x minus 5 x cube minus 5x plus 1 is same thing as x plus 11. Okay, times x square plus 6x plus 14 mod 17. Now you can check that, because x plus 11 is equal to 0 will give you x is equal to minus 11. 17 minus 11 will be nothing but 6. So this coordinate you are getting 6 comma 0, x equal to 6. Okay, so this is possible. Let me give you a few more examples. Now if you take the curve E2 with y square is equal to x cube minus 4x plus 1, this is again non-singular. So please do verify all these things, whichever I am saying, that you verify that this is non-singular over f17 with 24 points actually on the curve. So I can list these points 0, 1, 0, 16, 1, 7, 1, 10, 2, 1, 2, 16, 3, 4, 3, 13, 4, 7, 4, 10, 5, 2, 5, 15, 10, 3, 10, 14, 11, 8, 11, 9, 12, 7, 12, 10, 13, 2, 13, 15, 15, 1, 15, 16, 16, 2, and 16, 15. These are all 24 points. Now E2 contains no points for which y component is 0. You can see that there is no point with y component 0. In fact, since x cube minus 4x plus 1 is irreducible in F17x. Therefore, no point with y coordinate 0. Okay. Okay. So now I will give you another example. Another example is E3. The curve is y square is equal to x cube minus 3x, okay, plus 1. So this is also non-singular curve. You can verify over F17, and there are 19 points total. We can mention 0, 1, 0, 16, 1, 4, 1, 13, 3, 6, 3, 11, 4, 6, 4, 11, 5, 3, 5, 14, 7, 0. You see one component with y component 0, one coordinate. 8, 8, 8, 9, 10, 6, 10, 11, 13, 0, another component with y component 0, another coordinate. 14, 0, another coordinate with y component 0. 15, 4, and 15, 13. Now, since x cube minus 3x plus 1 can be factored as x plus 3, x plus 4, and x plus 10 mod 17. That's why there are 3 points like this, and this with y component 0. Okay. Okay, so now I'm also want to give you another interesting thing. So I think this field we have taken is field with 17 elements. So it's a field. Now let us look at a even characteristic field. The characteristic 2 field, and see what happens. Let's do it in a separate page. This time, I take K to be field with 2 raised for n elements, and our curve is C y square is equal to x cube plus ax square plus bx plus c. Obviously, a, b, c belongs to K. So we can write down f of x comma y as y square minus x cube plus ax square plus bx plus c. Right? Now I can compute del f over del x. That turns out to be, when we differentiate with respect to x, this portion will be 0. This is 0. This will be b, right? This will be 2x, which will be 0 because characteristic is 2. This will be 3 times x square. 3 will be 1 modulo 2. So we are left with x square. So basically we are left with x square minusing same thing as plus b when we differentiate. Okay. Similarly, when we differentiate with respect to y, this will be 2y. 2 is 0 modulo 2. So this is 0. This portion is 0 anyway. So the whole thing is 0. Why? Because characteristic of the field is 2. Now, every element in F2n has the root, in fact has a unique root in F2n, right? In particular, so unique square root actually, unique square root F2n in particular x square plus b has the root h is equal to b raised to power 2 raised to power n minus 1, right? Because when we substitute it here, x, at place of h, it will be b raised to power 2 raised to power n, right? So this equation will be satisfied by, because any finite field will, any element of the finite field will satisfy the equation. So the root turns out to be this quantity. Now once h is this, I can substitute h in this equation and get the value of y. So it gives a unique solution for y as k is equal to h cube plus ah square plus bh plus c raised to power 2 raised to power n minus 1. Okay. So this implies that hk is a, because this is a solution of this equation, this is a point of singularity. It's a point of singularity, right? So therefore, C is never an elliptic curve over f2 raised to power n. So any equation of this form where the left hand side in the V star equation only y square is there, will over the field of characteristic 2, I mean the 2 raised to power n will never be a elliptic curve. So it must contain, so in order to be a elliptic curve, it must contain on the left hand side, terms like x, y and y, etc. Then only this will be an elliptic curve. Okay, so this is the idea. So basically, the V star equation, this portion, so this portion should be there, and this portion should be there for the field f2 raised to power n if it has to be elliptic curve. Otherwise, it will not be elliptic curve because the points will be singular point, right? As we saw. Okay, now let us take some more examples. Okay, some more example. F8 is f2 theta, where theta cube plus theta plus 1 is equal to 0. So this is the irreducible polynomial through which we can build the field with 8 number of elements. Suppose the curve is y square plus xy is equal to x cube plus x square plus theta. Okay. So let fx comma y is given as y square plus xy minus the whole quantity, but minus is same thing as plus because characteristic is 2. So this will be plus x cube plus x square plus theta. So I can compute del f over del x, which will be y plus x square, and del f over del y will be x. This implies that When we put these things equal to 0, we will get x equal to 0 and y is equal to 0, right? So it turns out 0, 0 is a point of singularity, but 0, 0 is not a point on E. I can put x equal to 0 and y equal to 0. You can see that it does not satisfy the equation. This is not a point on E. Hence, therefore, E is an elliptic curve over F8. Okay. And it contains 9 points. Let me list all those 9 points. Theta, theta square plus theta, 1 comma theta square, 1 comma theta square plus 1, theta comma theta square, theta comma theta square plus theta, theta plus 1 comma theta square plus 1, theta plus 1 comma theta square plus theta, theta square plus theta comma 1, theta square plus theta comma theta square plus theta plus 1. Okay, so it contains these 9 points. Okay, so let me take another example. K is equal to field with 9 number of elements built from F3 of theta, where theta square plus 1 is equal to 0, right? So this is a field with 9 number of elements. Okay. So our curve is y square is equal to x cube plus x square plus x plus theta over F9 we are looking at. So we write down f of x comma y as y square minus x cube plus x square plus x plus theta. Then del f over del x turns out to be x minus 1 is equal to 0, and we just see what are the values, and we also put del f over del y is equal to 2y is equal to 0. This implies that point of singularity turns out to be x equal to 1 and y is equal to 0, right? But again, you can check by substituting that 1, 0 is not a point on E. Is not a point on the curve E, right? Therefore, E is a elliptic curve. And it contains 8 points. What are those points? 0 comma theta plus 2, 0 comma 2 theta plus 1, 1 comma theta plus 2, 1 comma 2 theta plus 1, theta plus 1 comma theta, theta plus 1 comma 2 theta, 2 theta plus 2 comma 1, and 2 theta plus 2 comma 2. Okay, these are 8 points here. And of course, here E contains no point with y coordinate equal to 0, since x cube plus x square plus x plus theta is irreducible in F9x. Okay, so this is another example which I gave. Any question at this point? Yes.
No, sir.
Okay, fine. So you are understanding everything? It is okay, or
Yes, sir.
yeah. Okay, so now finally I would like to give some simple versions of the V star equation, and I think those are useful depending upon the characteristic, what kind of variations are possible. So let me write down these calculations for you. So this is known as simple versions of V star equation. If characteristic of the field K is not equal to 2, you substitute y by y minus a1x plus a3 divided by 2. Okay, we get y square is equal to x cube plus b2 x square plus b4 x plus b6, something like this we will get. Okay, if we also have characteristic of K not equal to 3, replace x by x minus 3b2 divided by 36. Okay, and y by 216. So we get, actually after this I'm skipping the steps. We'll get y square is equal to x cube plus ax plus b of this form. Okay, if characteristic of K is equal to 2, then the curve, then our curve E is equal to y square plus a1 xy plus a3y is equal to x cube plus a2 x square plus a4x plus a6. Okay, so this is the curve. If characteristic is 2, there are two cases. If a1 is equal to 0, replace x by x plus a2, and the equation becomes y square plus ay is equal to x cube plus bx plus c. This is known as super singular curve. Okay, and if a1 is not equal to 0, then we replace x by a1 square x plus a3 by a1 and y by a1 cube y plus a1 square a4 plus a3 square divided by a1 cube. Okay, and then with the equation will become y square plus xy is equal to x cube plus ax square plus b. This is known as non-singular or ordinary equation. In fact, I can summarize these things in the form of a table. So without loss of generality, so number of points, even if we do these transformation on the curves, the number of points satisfied by the first equation or the transformed equation remains the same. We say that without loss of generality. This is our field and this is our V star equation. Any field, V star equation is y square plus a1x plus a3y equal to x cube plus a2x square plus a4 x plus a6. Okay, then if characteristic A is not equal to 2 and 3, then y square is equal to x cube plus ax plus b is the equation. Then we use this kind of equation. If characteristic of K is equal to 2, there are two cases depending upon a1 is 0 and a1 is not equal to 0. In one case, it is y square plus ay is equal to x cube plus bx plus c. and this is known as supersingular curve. Right, and the second case is y square plus xy is equal to x cube plus ax square plus b. This is known as ordinary curve. Right. Finally, when the characteristic of k is equal to 3, equation is y square is equal to x cube plus ax square plus bx plus c. So this is the basics transformation or simple version of the V-star equations depending upon the characteristic of the field. Okay. So any question at this point? I think I am done with today actually. I've given you the basic idea about the V-star equations, about these curves, and I think yeah, about these aspirational points. So we'll talk about the group and other things in my next class. Okay. Okay. So that's all for today. If you have any question. Yes, Ashish, Ajit, Praveen, any question or is it okay?
Also, no question.
I don't have any.
Okay, thank you. So we'll meet in the next class then. Bye.